Hi, I'd like to get like to discuss group theory. Actually, I want to get into linear abstract algebra a little bit. But beginning with that, you need to do group theory a little bit. So I just want to do a quick thing today, just about group theory. Groups. Okay. Well, let me just say an introduction quickly. The groups are self-contained things that you would say A and B is part of a group. And you have some operation. You could have either multiplication or addition or something or other. Or define your operation however you want it. But whatever your operation is, it works on elements in the groups, and what's inside the group has to stay there. Say it's multiplication. So if you have A and B are part of the group, then A times B has to be part of the group. And every element has its inverse, meaning to say, let's say an element A, you need to be able to get to the to 1 from that, the identity element. So let's say you have A as a part of the group, well then A inverse also has to be part of the group. Okay, that's basically what groups are. So A inverse is part of the group. If A is part of the group, A inverse has to be. And the simple way of saying that, and that's going to be important for the video, is that A times B inverse, B in itself inverse, that's going to be part of the group. That'll be that's going to be that'll be part of the group. Also, let's say you have a subgroup. What's a subgroup? Well, a subgroup is just what it sounds like. It's a group inside of this bigger group. But the subgroup has that important quality that it actually has all of the characteristics of the group, of a regular group. Let's say whatever's inside the subgroup has to stay there. If it's A and B is part of the group, then A times B has to be part of the group. And AB inverse also has to be part of the group. That's the important thing about it. So I wanted to discuss today is the idea of a homomorphism, which means it's basically like a function. Sort of, it generally means like you have, let's say, a function. It can go to, if you have an element, it goes to one other element in your, let's say let's say you have an element in your group G. Well, it goes to an element in H, and you might have several elements in G that by this function they actually go to H. To the same element in H. It might be, in other words, there might be like a V-shaped type of thing. They might all be coming to one element, or just a smaller number of elements. That's called a homomorphism. And it basically looks like an algebra. F of A equals F of A plus B together is the same thing as F of A plus F of B. So I wanted to discuss the idea of a subgroup of, let's say you have a homomorphism from G to H, and H is a completely different group, right? It's not a subgroup, but the interesting thing is, let's say you do have a subgroup inside of your G. Well, actually, that's what I wanted to show you. That's what I wrote just down right over now. Let's say you have a subgroup inside of G. You'll call that's going to be your K. Let's say your elements of your subgroup in K are going to be A and B. Well, you want to know what's going to happen if you do this same homomorphism G to H, you put them on those specific elements. Well, you'll get a subgroup of H. So let me just show how you see that. A and B, those are your elements of K. That's elements of K, which is a subgroup of G. So you know that F of A, because of this thing here, you know F of A is going to be in your H. F of B is going to be in your H. And F of A, F of B inverse are going to be in your H, because any subgroup of a group has to have the element, one element times the inverse of your element has to be part of that subgroup. So there's your one element there in H, one other element H. So together it has to be part of your H, your other group there. But now, what's your part of your K? Well, your K is things like AB also, but because it's a subgroup, it has to be AB inverse as part of your K. So you put the F on top of the A, F on front of the B, or F in front of that. You're going to have your elements of K, F of A or F of B, of AB inverse element of K. But that's what you see here, is that this is the same thing as that. So anytime you have a homomorphism from G to H, applied to, let's say, a subgroup inside of G, that's going to be a subgroup inside of H. Because you see that's the homomorphism quality there, that f of A B inverse is exactly the same thing as, because it's being a homomorphism, f of A and f of B inverse. This is equal to that exactly. Okay, well, thank you.